Deinterlacing is the process of converting interlaced video, such as common analog television signals or 1080i format HDTV signals, into a non-interlaced form. Interlaced video frame consists of two subfields taken in sequence, each sequentially scanned at odd then even lines of the image sensor. Analog television employed this technique because it allowed for less transmission bandwidth and further eliminated the perceived flicker that a similar frame rate would give using progressive scan. CRT-based displays were able to display interlaced video correctly due to its complete analog nature. All of the newer displays are inherently digital in that the display comprises discrete pixels. Consequently, the two fields need to be combined into a single frame, which leads to various visual defects which the deinterlacing process should try to minimize. Deinterlacing has been researched for decades and employs complex processing algorithms. However, consistent results have been very hard to achieve. Background: both video and photographic film capture a series of frames in rapid succession. However, television systems read the captured image by serially scanning the image sensor by lines. In analog television, each frame is divided into two consecutive fields, one containing all even lines, another with the odd lines. The fields are captured in succession at a rate twice that of the nominal frame rate. For instance, PAL and SECAM systems have a rate of 25 frames s or 50 fields s, while the NTSC system delivers 29.97 frames s or 59.94 fields s. This process of dividing frames into half-resolution fields at double the frame rate is known as interlacing. Since the interlaced signal contains the two fields of a video frame shot at two different times, it enhances motion perception to the viewer and reduces flicker by taking advantage of the persistence of vision effect. This results in an effective doubling of time resolution as compared with non-interlaced footage. However, interlaced signal requires a display that is natively capable to show the individual fields in a sequential order, and only traditional CRT-based TV sets are capable of displaying interlaced signal, due to the electronic scanning and lack of apparent fixed resolution. Most modern displays, such as LCD, DLP and plasma displays, are not able to work in interlaced mode, because they are fixed resolution displays and only support progressive scanning. In order to display interlaced signal on such displays, the two interlaced fields must be converted to one progressive frame with a process known as deinterlacing. However, when the two fields taken at different points in time are recombined to a full frame displayed at once, visual defects called interlace artifacts or combing occur with moving objects in the image. A good deinterlacing algorithm should try to avoid interlacing artifacts as much as possible and not sacrifice image quality in the process, which is hard to achieve consistently. There are several techniques available that extrapolate the missing picture information, however they rather fall into the category of intelligent frame creation and require complex algorithms and substantial processing power. Deinterlacing techniques require complex processing and thus can introduce a delay into the video feed. While not generally noticeable, this can result in the display of older video games lagging behind controller input. Many TVs thus have a game mode in which minimal processing is done in order to maximize speed at the expense of image quality. Deinterlacing is only partly responsible for such lag. Scaling also involves complex algorithms that take milliseconds to run. Progressive source material. Interlaced video can carry progressive scan signal, and deinterlacing process should consider this as well. Typical movie material is shot on 24 frames s film. When converting film to interlaced video using Deinterlacing, each film frame can be presented by two progressive segmented frames. This format does not require complex deinterlacing algorithm because each field contains a part of the very same progressive frame. However, to match 50-field interlaced PAL/SECAM or 59.94/60-field interlaced NTSC signal, frame rate conversion should be performed using various pull-down techniques. Most advanced TV sets can restore the original 24-frame S signal using an inverse Deinterlacing process. Another option is to speed up 24-frame film by 4% for PAL/SECAM conversion. This method is still vastly used for DVDs, as well as television broadcasts in the PAL markets. DVDs can either encode movies using one of these methods, or store original 24-frame progressive video and use MPEG-2 decoder tags to instruct the video player on how to convert them to the interlaced format. Most movies on Blu-ray discs have preserved the original non-interlaced 24-frame motion film rate and allow outputs in the progressive 1080p 24 format directly to display devices, with no conversion necessary. Some 1080i HDTV camcorders also offer PSF mode with cinema-like frame rates of 24 or 25 frames. The TV production can also use special film cameras which operate at 25 or 30 frames. Such material does not need framerate conversion for broadcasting in the intended video system format. Deinterlacing methods. Deinterlacing requires the display to buffer one or more fields and recombine them into full frames. In theory, this would be as simple as capturing one field and combining it with the next field to be received, producing a single frame. However, the originally recorded signal was produced as a series of fields, and any motion of the subjects during the short period between the fields is encoded into the display. When combined into a single frame, the slight differences between the two fields due to this motion results in a combing effect where alternate lines are slightly displaced from each other. There are various methods to deinterlace video, each producing different problems or artifacts of its own. Some methods are much cleaner in artifacts than other methods. Most deinterlacing techniques can be broken up into 3 different groups, all using their own exact techniques. The first group are called field combination deinterlacers, because they take the even and odd fields and combine them into one frame which is then displayed. The second group are called field extension deinterlacers, because each field is extended to the entire screen to make a frame. The third type uses a combination of both and falls under the banner of motion compensation and a number of other names. Modern deinterlacing systems therefore buffer several fields and use techniques like edge detection in an attempt to find the motion between the fields. This is then used to interpolate the missing lines from the original field, reducing the combing effect. Field combination deinterlacing . Weaving is done by adding consecutive fields together. This is fine when the image hasn't changed between fields, but any change will result in artifacts known as combing, when the pixels in one frame do not line up with the pixels in the other, forming a jagged edge. This technique retains the full vertical resolution at the expense of half the temporal resolution. Blending is done by blending, or averaging consecutive fields to be displayed as one frame. Combing is avoided because the images are on top of each other. This instead leaves an artifact known as ghosting. The image loses vertical resolution and temporal resolution. This is often combined with a vertical resize so that the output has no numerical loss in vertical resolution. The problem with this is that there is a quality loss, because the image has been downsized then upsized. This loss in detail makes the image look softer. Blending also loses half the temporal resolution since 2 motion fields are combined into one frame. Selective blending, or smart blending or motion adaptive blending, is a combination of weaving and blending. As areas that haven't changed from frame to frame don't need any processing, the frames are woven and only the areas that need it are blended. This retains the full vertical resolution and half the temporal resolution, and it has fewer artifacts than weaving or blending because of the selective combination of both techniques. Inverse Deinterlacing. Deinterlacing is used to convert a motion picture source at 24 frames per second to interlaced TV video in countries that use NTSC video system at 30 frames per second. Countries which use PAL at 25 frames per second do not use Deinterlacing since motion picture sources are sped up 4% to achieve the needed 25 frames per second. If Deinterlacing was used, then it is possible to reverse the algorithm to obtain the original non-interlaced footage, which has a slower frame rate. In order for this to work, the exact Deinterlacing pattern must be known or guessed. Unlike most other deinterlacing methods, when it works, inverse Deinterlacing can perfectly recover the original progressive video stream. To Lesside-style algorithms, if the interlaced footage was generated from progressive frames at a slower frame rate, then the exact original frames can be recovered by copying the missing field from a matching previous next frame. In cases where there is no match, then the filter falls back on another deinterlacing method such as blending or line doubling. This means that the worst case for telecide is occasional frames with ghosting or reduced resolution. By contrast, when more sophisticated motion detection algorithms fail, they can introduce pixel artifacts that are unfaithful to the original material. For telecine video, decimation can be applied as a post-process to reduce the frame rate, and this combination is generally more robust than the simple inverse telecine, which fails when differently interlaced footage is spliced together. Field extension deinterlacing equals. Half-sizing displays each interlaced field on its own, resulting in a video with half the vertical resolution of the original, unscaled. While this method retains all vertical resolution and all temporal resolution, it is understandably not used for regular viewing because of its false aspect ratio. However, it can be successfully used to apply video filters which expect a non-interlaced frame, such as those exploiting information from neighboring pixels. Line doubling takes the lines of each interlaced field and doubles them, filling the entire frame. This results in the video having a frame rate identical to the field rate, but each frame having half the vertical resolution, or resolution equal to that of each field that the frame was made from. Line doubling prevents combing artifacts but causes a noticeable reduction in picture quality since each frame displayed is doubled and really only at the original half-field resolution. This is noticeable mostly on stationary objects since they appear to bob up and down. These techniques are also called bob deinterlacing and linear deinterlacing for this reason. Line doubling retains horizontal and temporal resolution at the expense of vertical resolution and bobbing artifacts on stationary and slower-moving objects. A variant of this method discards one field out of each frame, halving temporal resolution. Line doubling is sometimes confused with deinterlacing in general, or with interpolation, which uses spatial filtering to generate extra lines and hence reduce the visibility of pixelation on any type of display. The terminology line doubler is used more frequently in high-end consumer electronics, while deinterlacing is used more frequently in the computer and digital video arena. Motion detection equals, best picture quality can be ensured by combining traditional field combination methods and frame extension methods to create a high-quality progressive video sequence. The best algorithms would also try to predict the direction and the amount of image motion between subsequent subfields in order to better blend the two subfields together. One of the basic hints to the direction and amount of motion would be the direction and length of combing artifacts in the interlaced signal. More advanced implementations would employ algorithms similar to block motion compensation used in video compression. Deinterlacers that use this technique are often superior because they can use information from many fields, as opposed to just one or two. This requires powerful hardware to achieve real-time operation. For example, if two fields had a person's face moving to the left, weaving would create combing, and blending would create ghosting. Advanced motion compensation would see that the face in several fields is the same image, just moved to a different position, and would try to detect direction and amount of such motion. The algorithm would then try to reconstruct the full detail of the face in both output frames by combining the images together, moving parts of each subfield along the detected direction by the detected amount of movement. Motion compensation needs to be combined with scene change detection, otherwise it will attempt to find motion between two completely different scenes. A poorly implemented motion compensation algorithm would interfere with natural motion and could lead to visual artifacts which manifest as jumping parts in what should be a stationary or a smoothly moving image. Where deinterlacing is performed, deinterlacing of an interlaced video signal can be done at various points in the TV production chain. Progressive media equals, deinterlacing is required for interlaced archive programs when the broadcast format or media format is progressive, as in HDTV 576p or HDTV 720p 50 broadcasting, or mobile DVB-H broadcasting. There are two ways to achieve this. Production: the interlaced video material is converted to progressive scan during program production. This should typically yield the best possible quality, Since videographers have access to expensive and powerful deinterlacing equipment and software and can deinterlace at the best possible quality, probably manually choosing the optimal deinterlacing method for each frame. Broadcasting a real-time deinterlacing hardware converts interlaced programs to progressive scan immediately prior to broadcasting. Since the processing time is constrained by the frame rate and no human input is available, the quality of conversion is most likely inferior to the pre-production method. However, expensive and high-performance deinterlacing equipment may still yield good results when properly tuned. Interlaced media when the broadcast format or media format is interlaced, real-time deinterlacing should be performed by embedded circuitry in a set-top box, television, external video processor, DVD or DVR player, or TV tuner card. Since consumer electronics equipment is typically far cheaper, has considerably less processing power and uses simpler algorithms compared to professional deinterlacing equipment, the quality of deinterlacing may vary broadly and typical results are often poor even on high-end equipment. Using a computer for playback and/or processing potentially allows a broader choice of video players and/or editing software not limited to the quality offered by the embedded consumer electronics device, so at least theoretically higher deinterlacing quality is possible especially if the user can pre-convert interlaced video to progressive scan before playback and advanced and time-consuming deinterlacing algorithms. However, the quality of both free and commercial consumer-grade software may not be up to the level of professional software and equipment. Also, most users are not trained in video production. This often causes poor results as many people do not know much about deinterlacing and are unaware that the frame rate is half the field rate. Many codecs players do not even deinterlace by themselves and rely on the graphics card and video acceleration API to do proper deinterlacing. Concerns over effectiveness. The European Broadcasting Union has argued against the use of interlaced video in production and broadcasting, recommending 720p 50 fps as current production format and working with the industry to introduce 1080p 50 as a future-proof production standard which offers higher vertical resolution, better quality at lower bit rates, and easier conversion to other formats such as 720p 50 and 1080i 50. The main argument is that no matter how complex the deinterlacing algorithm may be, the artifacts in the interlaced signal cannot be completely eliminated because some information is lost between frames. Yves Farauger, the founder of Farauger Labs and Emmy Award winner for his achievements in deinterlacing technology, has stated that interlaced to progressive does not work, and advised against using interlaced signal. See also, interlaced video, progressive segmented frame, a scheme designed to acquire, store, modify, and distribute progressive scan video using interlaced equipment and media, DCDI by Farauger, display motion blur, refresh rate, HDTV. References. External links, 3-2 pull-down and deinterlacing, stream interlace and deinterlace, format wars EBU document. DVD progressive scanning deinterlacing and film-to-video conversion with respect to DVDs, frequently asked questions about deinterlacing, 100 FPS facts, solutions and examples of deinterlacing, http, wiki.videolan.org/ Deinterlace #appendix:\technical_summary, video cleaner, free open source video software with multiple deinterlacing options.